And I will talk about the second application of the PD result. I will call this corollary harmonically flat. That's how you produce a matrix with special asymptotics from just general asymptotic flat condition. Right? So you can see in this construction, the most important part is to keep or to deform to have non-native scalar curvature where the dominant energy condition is for the Riemannian case. And start with just a general asymptotic flat metric of this general definition I wrote you earlier. And you can actually somehow deform this a little bit. At infinity, which is also asymptotically flat, matrix G bar. So actually, how about let me start with zero scalar curvature, because in the previous corollary, we know how to deform from non-negative scalar curvature to zero scalar curvature. So let's start with zero scalar curvature. And then here you can find another matrix called G bar, which is scalar flat and harmonically flat, which we call, that means outside compact set is just conformal to the flat matrix with some conformal factor. So that's our definition of harmonically flat. And where U will have some expansion. And such that in a way, how these two matrices are related, they are related in a way, let me add something. So given any epsilon, any number, you can find out asymptotic flat matrix G bar, scalar flat, harmonically flat, such that the mass is arbitrarily closed. Right? So actually in the construction, you will see this matrix G bar is also close to original G in some weighted space, but I will not talk about that. The key thing in the proof of positive mass theorem is you construct a matrix of this special asymptotics, but you don't vary the mass too much. So this also gives you some kind of density result among the space of solutions of scalar flat matrix, right? So roughly speaking, that means the asymptotic flat matrix with special types, special asymptotics, is dense, right? So in some well-defined space of matrix. Okay. Right, so here the proof goes by we cut off the matrix. So we look at cutoff function. You can think about this chi is just a smooth function defined on the Euclidean space, which is radially symmetric. So this coordinate means the distance to the origin. So which smooth goes from 1 to 0. All right, so that's a common cutoff function used in mathematics. If you multiply chi by something, then you will keep the original information, but then smoothly goes to 0 outside some compact set. And we're going to do this for a larger and larger ball. So let's rescale chi, define this with the indices k, which means it's a family of cutoff function, which is only supported inside the ball of radius 2k, and it's 1 in a smaller ball, and goes to 0. All right, so, and you can easily compute by the chain rule. Right, so there's some uniform bound depending on k of the derivative. So what we'll be doing is we just cut off the matrix G originally, but we multiply by the cutoff function. So if you do that, you get 0 tensor outside the compact set, right? But this is not Riemannian matrix. But we want to somehow interpolate between G and the Euclidean matrix. So what G hat K over a ball of radius K, that's just the original matrix G, the background one. And then outside a larger ball is the Euclidean matrix. So of course, this matrix is as regular as G and is asymptotically flat, is even Euclidean flat outside compact set. But the problem is it may not satisfy the scalar curvature condition. If we just do this, use brute force, it doesn't necessarily have non-negative scalar curvature. So the idea is we can conformally change it. So now we want to solve U. How about let's denote the depend on each cutoff radius K, such that this after conformal change is scalar flat. So yes.
What do you mean by this big Z? The derivative in there.
Or it's just a covariant derivative, or usually in Euclidean space. So yeah, just the covariant derivative and the Hessian.
And C is a constant.
C is a constant. C is a constant independent of K. Right, so we actually, so here chi, you can think about everything is Euclidean, in Euclidean space, because that's where it is defined. And then it's just rescale such that you actually define the annulus region becomes a larger annulus region. So we are going to let K go to infinity. So K is going to be large, and let's just tell you the derivative of the cutoff function decays of this rate. Okay, yes?
Can you show that this interpolation metric will never be degenerate?
How about exercise? Is right, so you can always show it's positive definite, right? So it's always a Riemannian matrix. Right. So the thing is, there's a uniform lower bound on the eigenvalue. There's also a uniform positive lower bound on the eigenvalue, and then you interpolate U. It's easy exercise. Okay? All right, so now the question is, can we solve this conformal factor? So that goes back to the ODE result. So the thing is for large, for K, if K is too small, so if you cut off in a smaller region, it may not solve this one. But as K goes to 0, roughly speaking, if K goes to 0, the matrix will go to the original matrix. And we know the original matrix already has this condition, 0 scalar curvature. Right? So for K large enough, you expect you are able to, the scalar curvature will be very close to 0. If there's a small error term, you are able to reimpose this condition, 0 scalar curvature, 0 condition. Okay. So if you want to find out this UK, and remember we do the translation. So let's reduce to equation for the VK. We want right? here the Vk goes to 0. And the condition in order for the equation to be solvable is this term is small enough, has some decay. And the most important thing is more like this one is not too negative. In this case, we don't know the scale curvature of this G hat metric is non-negative, right? Otherwise, we can just take it. So we have to check this is not too negative. So what's this one? So if you think about scale curvature, it's more like a nonlinear equation on the metric components, the second order derivative on the metric components, you would think about you take two derivatives of it. Two derivatives of it, the G hat metric. All right. So inside above radius k is just the original metric G, which is scalar flat by the assumption. So this is just the scale curvature of the original metric in the K ball. And outside, the 2K ball is also 0 because outside 2K ball is just a Euclidean metric. So we are really looking at what happens between the annulars. Right, so here, over the ball is just a matrix G. This is the flat metric. Here is where you interpolate. And if you took two derivatives, you get one derivative. You get by product rule, you will have the term involving two derivatives of chi and two derivatives of chi, and which will give you the decay of c over k squared. But then you will see that two derivative term will combine with the difference of g and delta, which we assume by the asymptotically flat condition, it decays as well. So if you work that out, you'll find out this term is of the order k to the power minus n. All right. So this is, once you get that, we have to check this is not too negative in the LOP sense. So we need to compute this quantity, right? So that's the LOP known when P equals n to half. That's where the PD theorem required. But it's an easy computation, and you still have a lot of room. Even the derivative weaker than this one is still okay. So you will find out this goes to 0. So that tells you when k is large enough, remember this has to be less than some Sobolev constant, right? Which you can do by taking k large enough. So by PD theorem, UK exists, and you are able to solve the PDEs, which means you can find this conformal factor to make the conformal metric scalar flat. So that's the proof about you can reimpose the scalar curvature condition. But then we still have to check we don't perturb the mass too much. Right. So how about let me write. So I think that should be enough for me to show the mass is not the mass of GK bar, which will go, the mass will go to the original mass n. So remember, we can compute what's the mass of G bar, all right? So if you use the formula, the mass will have some contribution from U, and will have some contribution from G hat. But then G hat at infinity is just a flat metric, so it has no mass. So the mass all coming from the conformal factor and coming from the expansion. So if we, so we know UK has the expansion. And what will be the mass of this metric? It will just be 2AK. So originally you should have this 2AK plus the mass of G hat, but the mass of G hat is 0. It's just a Euclidean metric. All right, so we need to show okay, so that will be the plan. This is actually the key part of the construction. That's really the key. We want to be able to control the mass effectively in this type of cutoff construction. So let's compute what 2AK is. We have explicit formula that coming from the equation. The equation where V satisfy or where U satisfy. Okay, right. So this is coming from again just do integration, integrate over the PDE, and then using divergence theorem to rewrite the Laplace term as the boundary term at infinity, and that term give you the constant AK in the expansion, and then the rest of term will just integral of other term in the PDE. So this give you, so let me, okay. All right. So what's really nice here is when K goes to infinity, again, this recovers the original metric. If this is the original metric, which is scalar flat, and the corresponding solution, UK, when K goes to infinity, has to be 1, because there is some uniqueness of this solution. Right? Because for the original matrix is scalar flat, then you can just use conformal factor 1 to conformal change to make it scalar flat, a trivial one. Right? So the estimate of the PDE actually tells you VK goes to 0 in some norm. So from estimates, we can see the VK in the part which I will not prove, but then you will see so that's a byproduct from the PDE estimates. And the Vk, the solution in this norm, is controlled by this norm here. But then again, by the asymptotics of, by the estimate of scalar curvature, this goes to 0. Okay. All right, so put that together, that will guarantee the first term is going to be, will go to 0 when k is large. So this goes to 0. So let's read just by Holder inequality, right? You can write this product in terms of some LP norm of this term and LQ norm of Vk. If we work out that factor, you can choose the norm is this one, which is again controlled by the scalar curvature of G hat, and altogether this term goes to 0. So what we really need to pay attention to is this term, the scalar curvature of the cutoff matrix. Okay, and this, I'm going to show this also link beautifully the definition of the ADM mass with scalar curvature. Right, so we are going to show, I'm going to say, let's handle the last term. The scalar curvature of a cutoff matrix. So this really is just over the annulus because it's 0 elsewhere. And if you write down the scalar curvature in the coordinates, so now the notation gets a bit heavy, right? But this is the matrix. And scalar curvature is a second order differential operator on the matrix component. The leading second order term is of this type. And there will be some nonlinear term, which will be quadratic in the first derivative. So everything is in the integral. So this term is going to 0 as well, because if you work out this derivative, and because it's quadratic term, so it will decay faster than the corresponding volume over the annulus. So the volume, roughly speaking, grows like what's the value of annulus? It goes like k to the power n. But this term, if you work out asymptotic flat condition and also the cutoff thing, it's going to decay faster. So the integral together, this will go to 0. So really the key thing is here. And if you do divergence theorem for the matrix component, what you recover is really the definition of ADM mass. So now we have the two annulus component. So this is Bk, and this is a larger ball. So if we do divergence theorem, then we'll have a boundary integral on the ball Bk and the boundary integral on the larger ball. Plus, this quadratic term is going to be something goes to 0 sk. So let me use the little o. So So little o means it goes to 0 as k goes to infinity. Or how about just lower the term. So you can see that's exactly the definition of the ADN mass. Right, so there's a summation. Over the finite sphere, the ADN mass will take the radius to infinity. But here we are doing this over actually two matrices. The original one, on the small ball, on the small sphere, the matrix is the original one. And over the larger ball, the matrix goes to Euclidean. So this is 0. That's the quantity of the Euclidean, the mass of Euclidean matrix, which is 0. And this term will go to the corresponding term of mass. So up to the normalizing thing. So this term will go to So there's a minus sign which cancels out the minus sign in the definition or in the computation of 2ak, which finished the claim. So what really compute here is saying we are doing some deformation in a way the mass is continuous. Okay? So let's finish the proof. So if we put together the corollary 1, remember the mass decreasing corollary, and the corollary 2, the harmonic flat corollary altogether, that's the statement due to Schoen and Yau. In the very original paper of the positive mass theorem in 79 and 81, in those two papers, what they do so if you start with a possible counterexample to a positive mass theorem with negative mass, and they are able to construct another asymptotically flat metric with 0 scalar curvature and harmonically flat and negative mass. Zero, yes, thank you. Okay. So how to put these two corollaries together? So the first one is we start with a metric with non-negative scalar curvature, and remember we can decrease the mass if it's not the scalar curvature is not identical to 0, right? So if it's not identical to 0, then we can conformal change it to make a scalar flat, and that will further decrease the mass. So it will be more negative. And now we can start with a metric of scalar flat, 0 scalar curvature, and we do this more technical construction, a harmonically flat construction. And we can choose the mass to be deformed arbitrarily small. So we can make a mass deformed arbitrarily small, so if the mass is negative, we can deform very, very tiny, such that after deformation, the mass is still negative. Okay? Questions? Yes?
Question, for instance, when you have this term derivative of g squared, right? I mean, naively looking at the top for the metric, I would say it goes as 1 over k squared. So it's not clear to me how.
So that's coming from the asymptotically flat condition, right? So the matrix, the derivative actually goes like a minus q minus 1. And q we assume to depending on the dimension. So that's where all the subtle conditions come in to make the PDE works. Yes. Yeah. Good point. All right. So, yes. Yes.
I just wanted to ask about that inequality between dk and the norm 2n minus 2 and the scalar curvature. I think you told us you'd give it without a proof. Can you tell us a little bit how?
Right. Right. So that's really coming from the estimate using the Sobolev inequality, which I wrote down, but I didn't. And that's coming from if you integrate the equation of v. So I just quickly give you the idea, right? So this we want to say y v is controlled by h, right? So the corresponding term there. So. Oh, sorry. Right? So let's integrate this equation. Multiply v and integrate it. So you will get this called Dirichlet's energy is controlled by f v squared and minus v. And then you use the Holder inequality to decompose the product. And right, so, and this one, for example, can be controlled by the negative, only the negative part, because if the positive part will only be even smaller, right? So altogether that will give you some LP norm. So if you work out a factor, that will be right. So that's for the Holder inequality of the first term. And the second term, you do the same thing, the Holder inequality, and that will be okay. All right. Now the key thing is okay, right. So zoom in your eyes or zoom out. So I will write. So there will be some factor which you have to work out. Otherwise, this just I'm writing to is not right. Yeah. So the thing is, you want to estimate the v to this norm, right? But here we use the Sobolev inequality. Remember, the Sobolev inequality tells you the v to this power can be estimated by the Dirichlet's energy. All right, so you have v squared of that norm, and then you have, so this is square, there. And then you use the Cauchy-Schwarz inequality to decompose it, right? So you can decompose this into some constant times the h norm, and then make it this very small factor times the norm will be observed to that side. So that will be then the standard PT technique. All right, sorry if you cannot see. Okay, all right, so let me maybe do the same board trick again to write below it. And so this theorem was done by Schoen and Yau decades ago, but together with a more recent observation due to Lohkamp, it actually tells you furthermore, you can do some further really magic deformation, which will lead to the first part I mentioned, or the second part I mentioned. You are able to somehow do some compactified procedure. All right. So this is an observation. So the proof, though, is also simplified. So you can find out proof in Schoen and Yau's recent paper, but it was known, the simplified proof was known earlier. And so from that metric, we are going to do some further trick to produce a positive scalar curvature metric on a compact manifold. So let's start with, again, the assumption if we have asymptotic flat and non-negative scalar curvature and mass is negative, so there exists a closed manifold of this topology. So that's coming from some closed manifold connected some with the torus, n-dimensional torus. Okay. All right. So now we can, using Schoen and Yau's observation, first we know there's already another metric which has zero scalar curvature, harmonically flat with negative mass. So G is harmonically flat, means it's conformal to the Euclidean metric outside the compact set. Okay, and it's zero scalar curvature. That means with respect to the Euclidean metric, U is harmonic. Right, so again, outside the compact set. And U has an expansion, right? It's a harmonic function, exactly harmonic function. And U has an expansion. And the expansion, this term will correspond to the mass, which is n over 2. And n is negative. So that's a consequence from this Schoen and Yau's deformation. Right? Okay. And so now let's draw, so U is not really radially symmetric, right? It's really look like a Schwarzschild matrix, but it's not, right? So there's a lower term. But just for demonstration, let's still draw graph of U in the radial direction. Just pretend it's rotationally symmetric. At least that's true for the top order terms. And U goes to 1. Right? That's all building in our deformation. We're looking for the conformal factor goes to 1. So this is the number 1 of the value of U. And we know U goes to 1. But the next term is negative. So you actually know it goes to 1 from below. It's less than 1 where x is large. So this is a graph of U. And it's really only defined outside the compact set. Right? Conformally flat means it's only defined outside the compact set. That's okay. We just look at really near infinity. And then the Lohkamp's trick is, how about let's cut it off just by some number. So since U goes to 1 at x goes to infinity, you know there's a number epsilon, say epsilon 2, such that when x is large, u is going to above that number. Okay. And then by maximum principle, because it's harmonic over the region, you know there's no interior maximum of the function u, so it has to below some constant, say 1 minus epsilon 1, right? And we can find this radius called sigma 1, sigma 2. So this is just a function property of this conformal factor u, the harmonic function. So what this says is there exist numbers okay? All right, and u is a harmonic function. So now if we define so if we define the function which coming from, really you take in this part of the function u, but then you extend by constant. So which means when u, but it's just original harmonic function, and this replaced by the minimum of ux. Okay. And the PD theorem tells you if you have harmonic function, two harmonic function, if you take a minimum of it, you produce a so-called superharmonic function. From the picture, you can see somehow it looks like a convex down, right? And which means this equation is superharmonic. So this means the Euclidean metric. Okay. So superharmonic is good because if you plug in to the equation for the scalar curvature, there's a minus sign in front of it. So what you get is actually a conformal factor which will produce non-negative scalar curvature. Okay. Of course, there's a subtlety. It's not smooth, right? There's a corner when these two functions meet, but you can mollify it. You can use smooth modifier around the corner. So say you tilt, right, say so if you do modify, you have to get up the radius a little bit. But then inside, in between, is right? So this altogether tells you you can produce as a G tilde matrix, right? Which is outside the compact set, outside and this is just original G. which has non-negative scalar curvature and outside the ball of radius b sigma 2 plus epsilon, this will just be a constant multiply the Euclidean matrix. So it's just a rescaling, trivial rescaling. So of course, all the curvature still vanish, right? So this is Euclidean, isometric to Euclidean. Okay. So what this tells you, we find a matrix from this construction, which really is really true flat, Euclidean flat outside some ball. And then inside, there'll be something coming from the G of the original matrix. Okay, and this will, by identify, you have a big Euclidean box named 2 infinity, then you just by identify the opposite sides of the big Euclidean box, so you can construct a quotient map which make it a torus here, and then there's a ball removed, but then you connect it some with the original piece from the asymptotically flat manifold. So, and this, the quotient map, give a corresponding quotient matrix G tilde on this compact manifold, and which will be non-negative scalar curvature. Okay? All right. And then we have non-negative scalar curvature, but the statement tells you we need to have a positive scalar curvature. That's important in the minima surface argument.
We need to raise it.
Yeah, so let me write this last one. So this to perturb leads to have positive scalar curvature is earlier result due to Kazdan and Warner. Yes. Yes.
Excuse me, I didn't get what is your quotient map?
A quotient map is so you cut off this big Euclidean box, right? Then you have in this two-dimensional picture you have 4 sides. Then you you identify these 2 sides. You glue them, and then you identify these 2 sides. That's how you, in the geometry course, you how to construct a torus, right? You identify these sides and then identify the other side, right? But in higher dimension, there's a corresponding thing. Okay? Yes?
Everything all right?
Yeah, thank you. All right, so then I will just say in words, there's a result of Kazdan and Warner, which they intensively study how do you deform scalar curvature or how do you prescribe scalar curvature. And the result tells you you can make it positive scalar curvature. You can make it strictly positive scalar curvature unless the closed manifold is Ricci flat. On the other hand, the manifold we construct will not be Ricci flat because we already know it's harmonically flat outside compact set with negative mass. So that's some Ricci curvature you can compute explicitly. So if the mass is negative, it's never Ricci flat. Thank you. So let me write down. So this is actually true for any closed manifold, but let me write it down. Specifically for this setting, So it's by studying the eigenvalues of the conformal Laplacian. So, but I think Justin will also mention a result due to Fisher and Marsden, which they use a different approach to have application, which in particular include this result. Okay. All right. So I will use the last few minutes to talk about rigidity, and we actually have almost all the ingredients ready. And the rigidity tells you what happened when the mass is 0. Okay? So rigidity will say, so if mass is 0, then it actually has to be the flat case, the Euclidean. The Euclidean Rn. So which is quite strong, right? In particular, implied there's no topology. All right, so by the mass decreasing corollary, if the scalar curvature is positive somewhere, then you can do conformal change to decrease the mass. But if the mass is already 0 to begin with, that means you get something of negative mass, right? So assume we have proved the inequality statement. We know there is no asymptotic flat metric negative scalar curvature with negative mass, right? So we may assume. All right, so the next is to prove it's actually Ricci flat. So this by consider a small compact deformation. H now stands for symmetry to tensor, and T is just a real number, very small real number. So you're looking at small deformation of the original matrix G, and H is compactly supported. So we are eventually going to plug in H to be a Ricci of the matrix G, the Ricci tensor. And so this does not satisfy the non-native scalar curvature condition. But again, when T is small, there exists a factor, conformal factor, okay, that would be the same PD argument. All right, so now the key thing, I will not do the computation, but the key thing is you compute the mass of this family of deformed matrix. So each one has 0 scalar curvature, asymptotically flat, so the mass should be non-negative by the non-negative positive mass theorem. But then we know when T is 0, so this will just be the original metric, which has 0 mass. All right, so that means if you do the first variation, or do variation of this, it's going to be non-negative, right? Because you get a critical point is actually a global minimum. The local minimum is good. Oh, sorry. Yeah, no. We actually just need a critical point. But on the other hand, compute out what's n, the mass of this family of a matrix. And remember, that comes from the expansion in the conformal factor and the mass of GT, which is 0, right? Because we choose H to be compactly supported. So that will be the mass of this. It's going to be 0, and the expansion from the conformal factory.
Sorry, why is
Yes.
the derivative 0?
Because this is a global, so at 0, mass it has a local minimum.
Oh, because you
It's
know it
assumed-
cannot be negative.
Yeah, we
So
assume.
you're using the
Right. So assume we have proved the non-negative mass theorem. Okay. So that's the formula for the mass of this family of matrix. Now we do derivative at t equals 0, but this we choose H to be compactly supported, right? So this is just the mass of the original matrix, which is 0. So it does not depend on t. So we only have the derivative force on this integral term. So now we carry a derivative inside. So we have the derivative on scalar curvature that will give you a linearization of the scalar curvature. We just talked about this in the morning. And then we also, by product rule, we have a derivative on u and evaluate at t equal to 0. But that term is gone because we assume G0, which is the matrix G, is scalar flat. And similarly, a derivative on the volume form will vanish. So through this computation, you'll find out this will be linearization of scalar curvature, where right, so there's 3 terms, but then the first 2 terms are divergence. So once you divergence, then you do divergence theorem that give you a boundary term, but H is compactly supported. So these 2 terms are gone. The only thing left is really H in the Ricci direction. But let's show you this quantity has to be 0 for any choice of H. And then now you can see that means the Ricci must be identical to 0. Okay? So what this tells you, the 0 mass matrix must be Ricci flat, and then there's also a theorem tells you asymptotic flat, Ricci flat matrix is Euclidean space. So in 3 dimensions, it will just coming from the classification of the constant sectional curvature matrix, right? Because Ricci 0 implies the sectional curvature is 0. In higher dimension, there's a more sophisticated argument to show that, but I'm out of time, so I will stop there. Thank you.